Hi, my name is Bruce, and today I will be presenting our work on running experiments in congested networks. This is joint work with some awesome collaborators from Netflix and from Stanford. So when we do networking research, we want to know whether or not a new algorithm will work well in practice. And in order to do this, we want run A/B tests, or randomized experiments, where we run this new algorithm on live traffic and see if it actually works better or not when it encounters all the weird stuff that goes on in the actual internet. These are just a few of the many papers published over the last decade that use A/B tests. There are many more unpublished tests. For instance, Netflix runs an A/B test for almost every single change it makes to its production network. So what is an A/B test? In an A/B test, we have some new treatment algorithm, and we want to compare this treatment algorithm to some existing control algorithm. In order to do this, we split up the traffic into two groups randomly, a treatment group and a control group. We apply the new algorithm to the treatment group, we run it for a while to collect some data, and then we look at what happens. In this case, the treatment algorithm would get better performance than the control algorithm, and so we would say that the new algorithm improves performance. This statement, that an algorithm improves performance, is a generalization. We're using the results of a small A/B test to decide what would happen if we were to go and we were to deploy this algorithm everywhere. This is a fine generalization to make, but it requires assumptions. And one of the big assumptions is that the outcome of one unit in the test doesn't depend on the outcome of the other units in the test. This assumption is called interference. If we think about it for a while, it's clear that interference must exist in congested networks. We have treatment algorithms and control algorithms, and they use the same networks, and they use the same queues, and they use the same links inside these networks. We know from decades of research on, for instance, congestion control fairness, that there are things the treatment algorithm can do to impact the control algorithm. For instance, if the treatment algorithm uses more bandwidth, there will be less bandwidth available for the control algorithm. And if the treatment algorithm does something that decreases queue lengths, then the control algorithm will also experience improved queuing delay. This is clearly interference, but we still use A/B tests to evaluate algorithms in congested networks. So this interference raises two questions. One, does this interference matter? Does it matter enough that it would affect the decisions we make and the algorithms we deploy? And two, if it does matter, what can we do about it? Our goal in this paper is to answer both of these questions. And we start with describing an A/B test we ran that shows that interference can really make the result of A/B tests very misleading. The treatment for this experiment was bitrate capping. In response to COVID-19, Netflix and most other large video services worked with governments to reduce load on the internet and make the internet more stable when people started working from home. Video is typically encoded at a number of different quality levels, and with bitrate capping, we took the highest qualities, the ones that also tend to be the largest, and just stopped serving them. So let's imagine what would happen if we ran an A/B test to measure the effects of bitrate capping. And let's imagine that all of the traffic is running on the same network over the same congested link. With bitrate capping, we would send less data into the network, and because this link is congested, maybe with bitrate capping the link would become uncongested. So there would be two effects of bitrate capping here. The first effect is that we're sending less data into the network, and the second effect is that this causes less congestion. Now let's imagine what would happen if we ran an A/B test. We would cap some fraction of the traffic to this link, and let's imagine that the control traffic wouldn't be affected. So if this were the case, we would correctly see that the capped traffic uses less bandwidth in our A/B test, right? Because here the capped traffic is using half of the traffic of the control traffic. But what we would not see in an A/B test is this effect on congestion, right? Because both the capped and the control traffic are using the same link, which is not congested. Another possibility is that the control traffic would notice that there's now a little bit of free space on this link, and it would start sending faster, it would start sending higher quality video, and it would fill up the link and recongest it. If this were to happen, we would again see that the capped traffic uses less bandwidth than the control traffic, but now it looks like it uses way less bandwidth. It uses like a third of the bandwidth instead of half of the bandwidth. And again, we would miss this impact on congestion, because here both the capped and the uncapped traffic are using the same link, which is congested. So in both of these A/B tests, we haven't really figured out what happens when we do bitrate capping. We've totally missed the impact of congestion, and this is because of the interference between the treatment and control. But we do want to measure what happens when we cap traffic, so now let's introduce a bit of formalism to help with this. So let's imagine we're back in this setting where the control traffic is going to use up whatever free bandwidth is available from the cap traffic. This is what the bandwidth usage would look like. On the x-axis, we have the fraction of traffic which is capped. On the y-axis, we have the bandwidth used. This pink line is the bandwidth used by the control traffic, and this purple line is the bandwidth used by the capped traffic. What we want to measure is the effect of capping, which is the difference between when 100% of traffic is capped and when 100% of traffic is using the control. This is called the total treatment effect in causal inference, and it's the effect of deploying bitrate capping. When we run an A/B test, we don't measure this. What we measure is one point on this graph. We pick some point on the x-axis and we compare the treatment and control at that point. This is not necessarily the same thing as the total treatment effect, and this is why A/B test results are biased when there's interference. But if we do want to measure the total treatment effect, we need multiple points on this graph. So if we were somehow able to run two simultaneous A/B tests, for instance, an A/B test with 5% traffic capped and 95% of traffic capped, then we could compare these 2 points, compare these 2 experiments, and use them to estimate total treatment effects. The problem is that typically this is hard. Typically we don't have isolation between A/B tests, and so we can't sort of run 2 A/B tests at the same time without impacting each other. However, we got very lucky and we found a very special location at Netflix which allowed us to do this. This location had a pair of very reliably congested peering links, where every night, during the peak hours, these links would become congested. The traffic between these 2 links was also very well balanced, and we were able to run separate experiments on each of these links. What we did, we ran a 95% A/B test on one link, a 5% A/B test on the other link, and we compared the 2 results. We found that bitrate capping improves throughput and that A/B tests did not measure this. In each A/B test, bitrate capping appeared to decrease throughput by about 5%. But when we compared the 2 links, when we calculated the total treatment effect, we saw that bitrate capping actually improved throughput overall. We saw similar behavior for RTT. Capping increased RTTs in both A/B tests, but when we calculated the total treatment effect, we saw that capping actually improved RTTs overall. This experiment shows that A/B tests can be biased when running congested networks. And this should be really concerning. We make really important decisions based on the results of A/B tests all of the time. We make decisions about whether or not an algorithm works well, and whether or not it's worthwhile to invest time and money in deploying the algorithm, and maybe invest time and money in doing follow-up work on that algorithm. If we had made a choice based on this bitrate capping A/B test we just described, we might have been totally misled by this test and made poor decisions. But another thing we just saw is that we can run experiments which remove this bias. In our paper, we talk more about this sort of experiment. One type of experiment we can run is an event study. In an event study, we switch from running 100% of control to 100% of treatment and compare before and after. We can also run switchback experiments where we switch back and forth between treatment and control and compare the treatment periods to the control periods. Both of these let us get better estimates of total treatment effect, and we talk more about them in the paper, and we also talk about how to integrate them into existing deployment workflows. Any A/B test which we run in a congested network has the possibility of being biased, and we would encourage you to run more experiments to see if this bias matters for your A/B tests. We would also encourage new proposals for new algorithms to include the results of these experiments and measure things like the total treatment effect so we get a better sense of how the algorithm will work when it is deployed. We also think this paper really highlights the need for better experiment methodology for networks. We've proposed a few new experiments, but we haven't used that much information about networks and how they work in order to design these experiments. We wanted to call this area to the attention of the community in the hopes that we could improve this methodology together. In conclusion, there's a lot more work we can do with designing experiments for networks, and I'm really excited to see the sort of experiments we can run, the sort of algorithms we can build by using these experiments. Thank you.